Okay, this is class 14, part B. If you haven't watched part A, go ahead back and do that. Make sure you watch both parts. But I divided these up because they're different material, distinctly different, and it's easier to divide it up into two chunks like that. So today, the second part of class, we're going to talk about non-regular languages. And so far, what we've talked about is all entirely regular languages. And as a quick reminder, by definition, a regular language is one which is represented by a DFA. So if we have a DFA that defines a language, we know that language is regular. And also, since DFAs, regular expressions, and NFAs can all be converted from one form to another form, that means that if we have a regular expression, we have a regular language. If we have an NFA, we have a regular language. So all of them define that same family of languages, regular languages. But the question comes up, what about non-regular languages? Are there languages that you could never make a DFA for? Or are there languages that you could never make an NFA for? Or are there languages you could never make a regular expression for? Notice that's all the same question. So are there any languages that are not regular? And so we are going to answer that question today. And do they exist? Well, we'll get to that in a second. But first off, how do we tell if a language is regular? And one of the ways of starting with that is this concept of what are called the closure properties of regular languages. And to figure out what a closure property is, let's start with this question. So the question is, if we have language 1 and language 2, and those are both regular, meaning that we have a DFA could be made for language 1, and a DFA could be made for language 2, and both of those are regular, then is the union of language 1 with language 2 also regular? So we union those together, is that also regular? And the answer is yes. And actually, it goes beyond that. The union of any number of regular languages is always going to result in a regular language that results from the union of those. And that is a closure property of regular languages. In other words, the family of regular languages is closed under union. And notice that that concept is what the closure property is. In other words, if I have two regular languages and I union them, or any number of regular languages and I union them, I'm always going to get a new language that's going to be also a regular language. In other words, I cannot union regular languages together to get something that's non-regular. It can't happen. And now, if we want to think about how we would go about proving that, it's actually pretty easy to understand that by definition, regular languages is one for which there exists a deterministic finite automaton. So when I union two things together, well, I could say, well, unioning this language with that language, I basically can make an NFA that does that by creating a new start state, and then branching on lambda to the DFA for language 1, and then branching on lambda from the start state of that to language 2. And now I have an NFA that represents language 1 union language 2. And that NFA could then be converted to a DFA using that subset construction method that we had used previously. And now, since the result of that would be a DFA, that result would therefore have to be regular. So notice there's a really simple to understand proof, even though we didn't go through the formal steps of that proof here. Notice conceptually, you can take language 1 and union it with language 2 by making an NFA, and then you can take that NFA and convert it to a DFA, and then by definition, if we have a DFA, the language has to be regular. So that's the family of regular languages is closed under union. Now, moving on, there are some other closure properties as well. Union, intersection, concatenation, the clean closure, the positive closure, and complement. Regular languages are closed under any of those things. Now, the one that causes most people to be a little bit confused here is the complement. You say, well, the opposite of a regular language, maybe that could not be regular. But if you think about the way complement works, that means that any string that would be accepted needs to be rejected, and any state that would be rejected needs to be accepted. So really, you can just switch start states, final states with non-final states, make any final state non-final, make any non-final final, And now we have the complement of that language in almost a trivial way. So regular languages are closed under all of these. Now, if you wanted to think about, I'd encourage you, just like we thought about the process by which you would prove it for union, notice that you could have that same kind of thought process for how you would prove it for all of these other ones. We just mentioned the one for complement. And probably the one that would take the most thinking would be this intersection. But try to think through how you would prove each of those as closed for regular languages, as a closure property of regular languages. Might be something for the midterm there. All right, anyway. Before we go on to showing non-regular languages, though, I want to talk a little bit about a language as being classified as finite, infinite, or empty. So how do we figure out if a language is any of those? Well, if we have a DFA graph for any of those, for some regular language, if there's a path from the start state to a final state, the language can't be empty. In other words, if there's a way to get from start following some chain of arrows and get to a final state somewhere, the language cannot be empty. And then also, to determine whether it's finite or infinite, if any vertex on some path from the start state to a final state has a cycle, so if there's any state that has that state as a base of a cycle, then the language has to be infinite. Otherwise, it has to be finite. In other words, if there are no cycles along any path from start to a final state, it has to be a finite language. If there exists just one cycle somewhere on one of those paths, the language has to be infinite. Now, how does that help with us knowing if a language is regular? Well, one thing that comes to mind here is that all finite languages have to be regular. In other words, if you have a finite language, it has to be regular. In other words, you will never have any non-regular finite languages. And the reason for that is because you could always just make a bunch of, if it's finite, it might be very large, but you could always make a bunch of states that accept every one of those paths for every one of the strings in that finite language. Would always have to be regular. But that does not mean that every infinite language is not regular. So what do non-regular languages look like? Let's see if we can figure that out. So how can we tell if a language is regular or non-regular? And the first concept I want to introduce here is this, in order for us to figure this out, to prove if a language is regular or non-regular, is this concept of the pigeonhole principle. And that sounds a little funny, and we're going to come back to that in a second. Before we do that, I want to mention something, and that is that remember, the definition of a regular language is one for which there exists a DFA, but it is not considered a proof for us to try to make a DFA and fail at it. So in other words, you cannot say, this language has to be non-regular because I couldn't make a DFA for it. You need something stronger than to just say, well, I couldn't do it, because it could be you're just bad at making DFAs, or the language is complicated and you just can't think of the right way to do it. And so you can't say it's impossible because I couldn't figure out how to do it. You have to have something stronger than that. And that's where this pigeonhole principle is going to come in. It's going to allow us to definitively prove that certain languages are non-regular, that you could never make a DFA for them. Not that you just suck at making DFAs, or that you're kind of an idiot and you were not on your best game that day and you couldn't think of it just right, so you failed at making a DFA for it. We want to be able to definitively prove that it's impossible to ever make a DFA for this particular language. All right, so let's look at the pigeonhole principle. Now, first off, if you look on the dictionary and look up what's a pigeonhole, that's a good thing to answer. So to answer that, looking in the dictionary, we get this. A pigeonhole, and there's the phonetic pigeonhole. That's a noun, and it means a small recess for a domestic pigeon to nest in. In other words, if you've ever looked at nesting boxes for pigeons, there's kind of like this grid, almost like a bookshelf with little boxes, and the pigeons go in there and they make nests inside of there and lay eggs inside the nests. But it's also come to mean a small compartment that's open at the front for forming part of a set where letters or messages may be left for individuals. So you think of like a mailroom, it's like, or if you've ever been at a hotel, especially like a a historic hotel, behind the desk they have a bunch of little boxes for each of the rooms where letters can be stuck for each of the room numbers for stuff to be delivered. You might also think of pigeonholes as being for work things where you have like an in basket and you sort things into different categories of this is bills and this is receipts and this is those are also kind of a pigeonhole. Now, so I notice that there's some cubby hole, compartment, slot, locker. The pigeonhole can also be used for, in a general sense, for a broad category that you sort things into. But let's think about it in terms of these compartments that you're using to stick items into these compartments. Now, that doesn't, not the pigeonhole principle yet, but that gives us this concept of what we're talking about. We're talking about these little boxes that we're going to categorize things into. Now, the pigeonhole principle basically states something that's remarkably simple, but has some far-reaching, surprisingly far-reaching consequences. And that is, the pigeonhole principle states if you have n objects and you place those n objects into m containers, so every object has to go into one container, some container, and the number of objects is larger than the number of containers, then we can deduce from that that at least one container has to contain more than one object. So in other words, let's say we have 100 pigeons and they all fly into, let's say, 99 containers, and they all went in somewhere. 100 things went into 99 spaces. Then one of those containers has to have more than one pigeon in it at that particular time. Now, they all could have gone into one, but that still means that one of them has to have at least more than one. So in other words, you can't fit more objects into containers than you have containers unless one of the containers has more than one object stored in it. And that's a really simple concept. It's really easy to understand. It's very easy to kind of comprehend that. But it can be used to prove some fairly remarkable things. And we're going to use that concept to prove that some languages are, in our case, we're going to use it to prove a very specific language is not regular. All right, so let's do that. All right, so here's an example proof. And we want to show that a to the n, b to the n, where n is greater than 0 is not regular. Now, let's first make sure we understand what this language looks like. And that basically is saying a string of a's that is n a's long, followed by a string of b's that is the same number long, where the number is greater than 0. So in other words, we could have 1a followed by 1b, or 2a's followed by 2b's, or 3a's followed by 3b's, but the number has to match. So it's a very simple language. Here's what some of the elements of it: A, B, A, B, B, A, B, 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 A, B, 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 and so forth. Always have the same number of A's followed by the same number of B's. So in English, that would be a string of a number of A's followed by a string of the same number of B's. So the language is very simple. It's also infinite. So it's a candidate for being not regular, but we don't know that it is yet. This seems like we should be able to make a DFA for this. It seems very simple. But let's prove that it is actually non-regular. All right, so that proof is going to look like this. It's going to be a proof by contradiction. And we are going to start with this assumption that L is, in fact, a regular language. And like most proofs by contradiction, we start with that assumption of the opposite of what we're trying to prove. So we're going to say we want to prove it's not regular. Let's assume that it is regular. And then what we're going to do is, because it's regular, there has to be some DFA for it, for that M, for that language. So in other words, it's a regular language, has to be a DFA for it. And that leads us to, there's an infinite number of values for n, because the language is infinite. It just says n has to be greater than 0. There's no bound on it. But there are a finite number of states for the machine M, because it's a finite automaton. That's part of the definition of what a DFA is. It has to have a finite number of states. So we have an infinite number of values that we can plug in for n, but a finite number of states. Now that fits the pigeonhole because we have more values for n than we have states in M. We have to, because this is infinite. We're fitting an infinite number of things into a finite number of states. That means that by the pigeonhole principle, there have to be distinct values that we would plug in for n, in our case, a to the I, aj, that end in the same state m. Because there's an infinite number of these, that means that there has to be different values of this that end up in the same state m. Again, fitting more things into than we have boxes into that smaller number of boxes. That means some box, some state m, or some state of m, has to have two different values that end up in it, because we're fitting an infinite number of things into a finite number of boxes, states. Now, that means that from that state, a to the I, b to the I has to end in a final state, because a to the I, b to the I is in the language. So a to the I, b to the I has to be in the language. That fits this. It's the same number of a's as b's. But since a to the j could also get us to that state, then b to the I must also end in a non-final state, because a to the j followed by b to the I is not in the language. So that, notice that we went from that state we were in, we used bi on both of those, so we end up in the same state, but it has to be both final and not final. And since the state reached cannot be both final and non-final at the same time, we now have a contradiction. That's impossible to have a state that we ended up in that was both final and non-final at the same time. So therefore, our assumption that L is regular has to be incorrect. And because that assumption has to be incorrect, therefore, our assumption was that L was regular, therefore L has to be non-regular, which means that, kind of to summarize, the language a to the n, b to the n, where n is greater than 0, cannot be a regular language. We can never make a DFA for that. And that's the pigeonhole principle is kind of what allowed us to prove that. The concept here is like, you know, I have a finite number of states, but an infinite number of values, so there has to be two values somewhere. We don't even have to know what they are, but there have to be two values here, that because we don't have to know what this DFA even looks like. We just have to know, well, we assume it was regular, so there is one. If there is one, it has a finite number of states, but there are an infinite number of values for n, and because we're now putting an infinite number of values for n, there have to be two of these that map to the same state. And then from that state we got to, if I consume b to the I symbols, that has to be a final state. But if I consume b to the I symbols, it also has to be a non-final state, and you can't have a state that's both final and non-final. It doesn't make any sense. Therefore, you can't have a DFA. And if you can't have a DFA, then it can't be regular. Very clever proof. And notice what's cool about this. We didn't even have to know what the machine looked like. We didn't have to know what state it was we reached to, a to the I, a to the j. We didn't have to know that at all. We just had to use this pigeonhole principle to know there has to be one. And if there is one, then this has to be true. And that can't be true. So this our assumption has to be incorrect. Okay, now that is actually an application of what's called the Pumpinglemma for regular languages. And what the Pumpinglemma is, it's kind of a generalized version of that kind of concept that can be used to prove a lot of different things. Now, we'll see the Pumpinglemma again later this semester because there's a Pumpinglemma also for context-free grammars, which we haven't gotten to yet. But the Pumpinglemma basically states the following. An infinite language is regular if it can be defined by a DFA. So we already knew that. That's kind of by definition. That if there is a DFA, that DFA has to have a finite number of states, n. Has to be a finite number of states or it's not a DFA. So both of those are kind of by definition of what it means to be a DFA. Now, since the language is infinite, some strings of that language L have a length greater than n. So if the language is infinite, there will be strings that are longer, have more symbols than the number of states we have. And for a string of length greater than n to be accepted, the walk through the DFA has to contain a cycle. And then by repeating that cycle an arbitrary number of times, we can yield additional accepted strings. So in other words, that's the pumping part. So we basically say, hey, here's a path from a start state to a final state. Along that path, there has to be a cycle if it's an infinite language. And I could repeat that cycle to get more and more and more characters in the string to get additional strings that have to be in our language. So think about that as pumping the length of the string up. We could repeat it once to pump once or twice or 3 times, and we're always adding symbols. Because this is a DFA, there's no lambda transitions causing it to have a cycle. It has to be associating that edge that it's traversing with a character. So we could repeat that 0 times or 1 time or 2 times or 3 or any arbitrary number to always have additional strings in the language. So that's what we used in that proof, previous proof, is we used a version of that Pumpinglemma. And the Pumpinglemma can be used to prove languages non-regular, and it's always a proof by contradiction like we did before. You assume that the language is regular. You assume that there's a DFA for that language. By the Pigeonhole Principle, then, if the language is infinite, then there have to be some strings with more symbols than we have states. And if that's true, then that has to have a cycle along that walk to that final state. And then we can repeat that cycle some arbitrary number of times. And if we can repeat that and pump it in a way that yields a string that is not in L, then we know that the language could not be regular because we have a contradiction. And that's essentially the way you'd use the Pumpinglemma, as you'd say. And that's what we did earlier. We said, okay, we had a to the I. Well, that a to the I, b to the I has to be in the language. But a to the j, which was maybe something different than I, repeating it a number of times, a to the j, b to the I, could not be in the language because those are different numbers of a's and b's. And so that's why that previous proof was sort of an application of this Pumpinglemma for regular languages. And the difficult part about using the Pumpinglemma to prove things is that we don't know what the actual DFA looks like. We've just made this assumption that there is one. And we don't know where the cycle is or what state it is because we don't have an actual DFA, because in most cases you couldn't create one anyway. If you could create one, then you know it's regular. But the part that makes it easy is we get to choose the string and get to decide how many times to pump that. And in our previous case, all that mattered with a to the I, b to the I, or a to the n, b to the n, was that we could get something that was a to the j, b to the I, or a to something other than n, followed by b to the n. And that had to end in an accepting state, but it couldn't. So the idea is you would use this proof in that same format that we used back here for anything, to prove any language that we have as non-regular. Now, a few of these to consider that I want you to think about is, what about a to the n, b to the m? In other words, there's more a's than there are b's. Is that non-regular? And if so, could you prove it? Or what about where there's a different number of a's and b's? In other words, we have a number of a's, we have a number of b's. They're not allowed to match. Is that non-regular? And could you prove it? The third one there is we have some string w that's entirely composed of a's and b's. But we want the it doesn't matter what order they're in. They can be in any order. And notice that's star, so that could include lambda. We want the number of a's to match the number of b's. Is that regular or non-regular? And then the last one is WW. So in other words, we have substring of a's and b's. And following that, let me reverse that. Following that is the same string of a's and b's. So in other words, AA would be followed by AA. AB would be followed by AB. So in other words, the first half matches the second half. So if you cut the string right down the middle, the beginning and end should match each other. And there would have to be an even number of characters. Can you prove that's non-regular? So I want you to think about how you would prove each of those using that Pumpinglemma that we talked about, using the Pigeonhole Principle that we talked about. How could you prove each of these as either non-regular or regular? Okay, last thing, again, I mentioned this in the previous video, but the midterm exam will be held in person. in ATC room 326, Advanced Technology Center 326, up on the 3rd floor, where we're regularly supposed to meet. It'll be held 1 week from today, meaning the 19th of October 2020, and it'll take the full time from 2 o'clock to 4:15. It is open book, open notes. You will not have access to the internet or electronics. It'll be a paper exam, so you'll take it all on paper. And a study guide is posted on the course site. And one thing about that study guide is there's 2 versions of that I'm posting. One that has no answers, and one that has the answers filled in. So what I would expect you to do, or what I think you should do to get your best performance, is go through the study guide, take the practice questions, try to fill in the answers, and then check the answer key. And if you're struggling with that or need help with that, I'm going to be in class in person on Wednesday from the normal class time, so 2 o'clock to 4:15, and I can help you with any problems that you've had on the homework or any problems that you're having with the study guide or questions that you have. Part of the study guide postings will also have in addition to the practice test and the answer key, we'll also have an outline of all the topics you should be familiar with. So you might want to look through that. Things that stand out as being you're a little fuzzy on, brush up on those things, and just make sure to come in and take that exam. Also, if you have an accommodation that you need, send me an email to remind me of that, whether that's more time or whether that is some other accommodation you need, bigger font size so you can see the test, whatever. Just make sure to let me know. Okay, that's it. So go through the midterm study guide and the practice questions for that. Make sure to stay safe, wash your hands, and wear a mask when appropriate. And I will see everybody hopefully on Wednesday for the study period. And then I hope, really hopefully, everybody shows up for the midterm. But I'll see you Wednesday, and if not, next Monday.